Okay, and from this month, we are going to, invite one, a speaker from, from Flinders University, and so first of all, welcome everybody on board, and I would like to, give a very brief introduction for our, speaker for this afternoon, and the topic of this seminar is the optimization of electrical machines for wide torque speed range, an example of axial-flux induction motor for the application of electric vehicles. And the presenter is Dr. Amy Memodi from Flinders University, South Australia. And Amy received his bachelor degree in electrical engineering from Shiraz University, Shiraz, Iran, in 2005. A master degree in electrical power engineering from Amir Kabir University of Technology, Tehran, Iran, in 2008, and the PhD degree from the University of from Malaysia, Kuala Malaysia, in 2013. His research interest is in areas where energy conversion and transmission play a major role, such as hybrid power networks, renewable energy systems, transmission and distribution networks, electrical machines and drives, as well as numerical methods in electrical engineering. In particular, he carries out the research in the area of electrical machines and power electronics for applications such as renewable energy, electric traction systems, and electrical drives for industrial applications. Currently, he is working as a lecturer at Flinders University. Dr. Memodi is a member of the Institution of Engineering and Technology and a chartered engineer. He's also a member of the Engineers Australia and the Chartered Professional Engineer. So now let's welcome Dr. Amy to give us, deliver a talk for us. Thank you, Dr. Amy.
Thank you, Mr. Chairman. Thank you for the introduction. So let me share my screen before I start. Yeah.
Sure. So before we start, I kindly suggest everybody can mute your speaker, and to guarantee our online seminar performance. And if everybody has questions, so maybe after this talk we can have very active and free discussions.
Can you see my screen?
Yes, we can see. Yeah.
Okay. I'll start. Hello, everyone. Before I start my presentation, I would like to thank the IEEE Industrial Electronics Society Western Australia section for arranging this seminar. My name is Amin Mahmoudi. I'm a lecturer at Flinders University in Adelaide, and I'm mainly active in the field of electric machines and drives. Today, I'm going to talk about optimization of electrical machines for wide torque speed range. In particular, I will discuss an example of axial-flux induction machine for the application of electric vehicle. This talk will take around 50 minutes to finish, basically. In this talk, I'll start with some introductory material on the optimization of electric machines to provide some background information. After that, I'll present the case study. I'll introduce the methodology for the optimization purpose, followed by the discussion around the analytical model, which I use for the optimization purpose. Then I'll bring forward the optimization problem for the case study. Also, I will discuss around the optimization results. Finally, I'll conclude the session. This slide lists the acronyms which I frequently use in my presentation. The first three rows are the acronyms for the machines often discussed in this presentation: IM, induction machine; AFIM, axial flux induction machine; RFIM, radial flux induction machine. FEA and AM represents the finite element analysis and analytical model, respectively. MTPA refers to the control strategy of the maximum torque per ampere. GA is a familiar term for genetic algorithm. These three highlighted rows are associated to the acronyms for the three different driving cycles that I use in this study: Highway Fuel Economy Test, HFET, New York City Cycle, NYCC, Urban Dynamometer Driving Schedule, UDDC. 2D and 3D refers to the two-dimensional and three-dimensional respectively that I will use in this presentation. As an introduction, let's see what literature survey tell us about the research and development, basically R&D in the field of optimization of electric machines. Several research studies have been carried out the design and optimization of electric machines, and then in all these work, or most of these work, generally the design and the optimization procedure are based on a rated condition for a single operating point of the motor rather than the actual working cycle of the machine. There is an issue with such an optimization approach. An optimization only performed on the rated condition might not yield to the optimum result the entire driving cycle of the machine. Also, it may not meet the requirements of the entire operating cycle. Examples for such applications are the electric motors for electric vehicles and generators in wind energy system. For instance, in the case of electric machine application, the motor during a city profile mainly works in low torque operation, which is far from the rated condition, as seen in this figure of the slide, basically. Mapping the two sample driving cycle of the left-hand side figure, JC08 and UDDS, into the torque speed plane shows that the operating conditions which happen around the low torques and speeds basically are far from the rated operating points. In addition to this, from the machine design point of view, the field of electromagnetics is considered mature and there is no big need for future researchers. However, the field of application is still so widespread that the new research and development efforts must be continuously taken. From the machine application point of view, utilization of the machine in different applications, for example, high-speed application, sets totally different boundary conditions than a typical industrial drive at a normal speed range. In former times, basically, optimal designs were found by just investigating the electromagnetic part, but nowadays, thermal analysis, rotor dynamics, heat transfer, and fluid analysis, control strategy, and power electronics all are also included for an optimal design. That is, as I mentioned, is far from the traditional optimization process. Based on what I have discussed, I believe that the disruptive innovation in the electrical machine design optimization for a specific application are motivated by emerging trends such as improvement in mathematical and computer science, which have embedded more detailed optimization scenarios covering more aspects of the physics. In order to investigate the consideration in design optimization of the electrical machines, I would like to present an example of optimization of an electric motor for wide range of operation points rather than the optimization of the machine for a single operating point. The application which I have selected for this purpose is the electric vehicle application. The motor that I have selected is axial-flux induction motor. I shall highlight that I will not cover all aspects of the machine design optimization which I mentioned in the introduction, but I attempt to give an idea of how a sample optimization is conducted. This slide here summarizes the entire story of this session. I'll go through the details in the next slides, basically. In this case study, I'll present the optimization of the axial flux induction machines for the vehicle applications. I'll discuss an optimization method for the motor based on the design parameters, control strategy, and driving cycle. I would also exploit an analytical model to solve the Maxwell equation in a short time. In fact, the analytical model enables a quick and reliable evaluation of the design parameters. The reduced computation time of the applied analytical method, of course, versus finite element analysis allows the implementation of a larger scale optimization. Genetic algorithm is also used as the optimization tool for this case study. Why I have selected the axial flux rather than a conventional radial flux motor? We know that the radial flux structure is commonly used structure of the electric machines, in which the flux is going to travel in radial direction. In axial flux structure, the flux travels in an axial direction. Axial flux machines have disc shape in contrast to the cylindrical shape of the radial flux machine. So they can be used as a hub motor inside the wheel of an electric vehicle. That's one important aspect. To highlight some further features of the axial flux induction machine, I have compared the performance parameters of two samples of 1 kilowatt induction machines, axial flux induction machine and radial flux induction machine. In addition to the shape factor that I mentioned, the axial flux induction machines generally have higher power density. It is observed by looking at the power to weight ratio and weight of the axial flux induction machine as compared to that of radial flux induction machine in this table for the same rating. Also, please note that the efficiency and power factor of the axial flux is comparable to the radial flux type of it. Anyway, I just presented this table to emphasize on some unique features of the axial flux machines. Please note that these listed motors or these listed specifications are different from the motor that I will present later for the optimization purpose. Just I present it because I had some information to share, which is related to the topic, basically. Okay, before a further discussion on this case study, it is important to know what methodology is used for our case study. Also, I would like to address why we use such a methodology. In addition to the shape factor that I mentioned earlier, the axial flux induction machines offer high starting torque, wide constant power region, short time overload capability, compact structure, high torque density, and fault tolerance, which make them suitable generally for an electric vehicle application. Generally, when you come up in an initial design of the machine, in this case, axial flux induction machine, it is then necessary to optimize the machine for achieving the high performance. In axial flux induction machines, a long calculation time is required, especially in optimization process, due to the necessity of the 3D simulation, 3D finite element analysis simulation. So this problem becomes even more severe considering the transient nature of the field development in induction machine. Therefore, a fast and accurate model is necessary for the optimization purpose. I have listed the current simulation approach. Looking at this approach, 3D finite element is not a feasible option, and the 2D FEA is still very time consuming. I'll talk about in details in later slides, but that's a problem with these methods. Designing methods based on the empirical data, like sizing equations, are considered a solution to reduce the calculation time, but they are highly prone to large errors due to the poor estimation of the equivalent circuit parameters. Analytical modeling of the machine is the most promising alternative for optimization purpose by offering the reduced calculation time and comparable accuracy versus 2D FEA, of course. The downside is that they don't often consider the saturation. In this study that I will talk, or this presentation, I have exploited an analytical method to solve the Maxwell equation, enabling a short-time performance prediction. And the model that I use considers saturation as well. I don't dwell on how the saturation is implemented in this session, basically, due to the time limitation, but I'll discuss the other aspect of the presentation. Okay. Before talking about the applied analytical model, I would like to briefly highlight the issues with our proposed analytical model. The motor under the study is an axial-flux machine which necessitates a 3D modeling. However, we must work on the 2D model in the analytical method, which introduce some issues, basically. To present the equivalent 2D linear model of an axial-flux induction machine, as seen in this figure, basically, it is assumed that both inner and outer radius of the machine are significantly bigger than its axial length, resembling a disc shape, basically. The 2D linear model is therefore obtained from the intersection of the model with the cylindrical surface with a mean radius of the machine, as indicated in the figure on top. The width of the linear machine, the extracted linear machine becomes equal to the actual length of the axial flux motor, and the depth of the linear machine becomes equal to the difference between the inner and outer radius of the axial flux motor. To see what happens in 2D as compared to that of 3D modeling, in this slide, I have compared the speed response of a 2D and 3D FEA for sample 1 kilowatt axial flux induction machine that I presented some of its specification earlier. As you can see in this figure, the proposed equivalent 2D linear model introduced some limitation in exact prediction of the motor performance. It is seen that the 2D model is not able to exactly predict the transient behavior of the motor, but gives rather reasonable accuracy in a steady state operation. It is chiefly because in 2D modeling, an infinite length along the radial direction is assumed. Also, the 2D modeling ignores the end binding effects. I also have included the comparison of the current and torque responses. Similarly, an acceptable accuracy in a steady state performance prediction is observed, but rather a poor prediction of the transient behavior is seen. Now, we have understand the limitation of the 2D modeling. So it's time to see what sort of analytical modeling we will be using and what trade-offs the applied analytical model is going to offer for our case study. First, I would like to know the trade-offs. So that's what I'm going to do. To do so, I need to implement the analytical model on a sample axial flux induction machine. This slide lists the main design parameters of an initial motor design for the EV application purpose. It's a 40 kilowatt motor, 8-pole induction motor. 40 kilowatt, 8-pole induction motor. So I use this motor for the validation of the analytical model and to check the suitability of the analytical model against the finite element analysis. To investigate 2D versus 3D modeling of the effects and suitability of the proposed analytical model, performance of the motor of this study is predicted using transient 3D and 2D FEA, as well as the analytical model. In this slide, the magnetic flux density inside the motor geometry extracted from the 2D and 3D FEA, and they are illustrated here. Looking at the magnetic flux density plots, a good match between 2D and 3D results are observed. And also to investigate the accuracy of the different simulation techniques, the performance parameters of the motor under the study is going to be estimated using different approaches against 3D FEA. In this figure, all the values are presented in percentage. Speed and current also are presented in per unit in percentage. To present the speed in per unit, synchronous speed is considered as a base value. To present the current in per unit, 3D FEA current is considered as the base value. Anyway, this figure presents the simulation result. For example, load of 200 Newton meter and 3 different speeds. So the results and the performance parameters are extracted for these 3 different speeds based on different approaches. The 3 different speeds are 750 RPM, 1500 RPM, and 3000 RPM. The simulation results illustrate that, as expected, the power factor, efficiency, and the speed of the 3D model are slightly less than the 2D model, which is due to the limitation of the 2D modeling, which we have discussed earlier. In this figure, also, there are 2 sets of analytical results. We have an initial sort of analytical result. In fact, in the initial analytical result based on the analytical model, we have corrected some of the results in order to consider the end binding effects to make that simulation result more realistic and closer to a 3D FEA simulation. So that's why I have named those analytical model as the analytical with end effect. Anyway, the analytical result with the ending effects provide a reasonable accuracy against the 3D FEA. And we will use the analytical model with end effect for optimization purpose in the future slides. In addition to the accuracy, the simulation time is also a very important factor when modeling an electric machine for optimization purpose due to the high number of required simulation. So in this table, a comparison of the calculation time for 3D FEA, 2D FEA, and the proposed analytical methods are also presented. Note that all these simulations are conducted on a similar computer with 128 GB of RAM. It is seen that the proposed analytical method takes only 0.34 seconds, about 1/8 of the single step to the FEA simulation, which is 2.7 seconds. Simulation time is 55 seconds in the 3D FEA for a single time step, which is again 160 times more than that of analytical model simulation time. The numbers are only for one time step simulation that I have presented here. I shall highlight that FEA of the induction machine necessitates a transient simulation as an induction machine, as in an induction motor. Basically, the operation speed is unknown value. So a transient should be completed to make sure we get the right result of the simulation. So to obtain the performance parameters of the motor in a steady state condition, simulation time is going to be extended to 224 minutes in 2D FEA based on around 15,000 mesh elements and 5,000 time steps required for this study, basically. Even if I look at these numbers for 3D finite element simulation, these numbers are going to be worse for a 3D FEA. Anyway, so the bottom line is that the comparison of these simulation times conclude that neither 3D FEA nor 2D FEA are practical options for the optimization purpose. So we have discussed the advantages and disadvantages of the proposed analytical method and also came to the conclusion that the analytical model is suitable for the optimization purpose as it provides reasonable accuracy in a short time. So we are able to apply the analytical model in an optimization. And this flowchart illustrates a simple process for the optimization process or purpose. We need to define the variables and assumptions for the optimization problem. Variables and constraints also are going to be fed to the analytical model, and the objective function is calculated in each optimization step. So that's how we are going to do the optimization. But before going to the optimization, after discussing the suitability of the analytical method, I would like to introduce the analytical method in more details for this study. The analytical method is derived based on the subdomain approach for our case study. This figure shows the exploited view of the under study axial flux induction machine. The 2D linear model is obtained from the intersection of the axial flux induction machine with a cylindrical surface with a mean radius of the machine. In the analytical model, knowing the structure and the current excitation of the machine, the Maxwell's partial differential equation in each subdomain could be solved. Writing the Maxwell partial differential equation of the magnetic vector potential results into the Poisson equation listed here. The geometry of the studied axial flux induction machine is divided into 5 sets of subdomains, including rotor and stator slots, slots opening for the rotor and stator, as well as the air gap. To solve the Poisson equation, I need to apply the applicable boundary conditions as per the motor geometry. The boundary conditions of each subdomains are achieved by considering the continuity of the magnetic flux and Ampere's law in the borders, which means, or it means that zero parallel magnetic field at air-iron boundaries and continuous magnetic vector potential at air-air boundaries. That's how I do it. After solving the differential partial equation in previous slide, the magnetic vector potential in a different subdomains or parts of the machine geometry is obtained. The general solution for the Maxwell partial differential equations of the magnetic vector potential for each subdomain are listed in this slide. In all these general formulas, the Fourier coefficients are unknowns. After applying the boundary conditions, a set of linear equations with 16 independent equations are obtained in which you can extract the unknown Fourier coefficients. Once the Fourier coefficients are obtained, it means that we have the magnetic vector potential distribution inside the motor geometry. A summary of what I have discussed is illustrated using block diagram in this slide. In fact, it is a flow chart of the process for obtaining the magnetic vector potential of different subdomains that I just showed. From the magnetic vector potential, the magnetic energy of the machine can be calculated. If I have the magnetic energy of the machine, the equivalent circuit parameters also can be calculated. In fact, when calculating the magnetic energy of the machine from the equivalent circuit, it should match to that of the values extracted from the subdomain method. So we shall be able to estimate the equivalent circuit parameters of the machine. Okay, I have been muted, yeah? Hello?
Hello? Hello?
Yeah, I received the text that I have been muted, yeah?
No, we can hear you.
No, we can hear you, yeah.
Okay, so I have not been muted.
No problem. Please continue.
Okay. Okay, can you see the slides?
Yeah, we can.
Okay, that's good. So I continue.
Yeah, sure.
Okay, yeah. So what I mentioned, that
Hello, Amy. I think now is muted again. So if you can.
okay.
Yeah, now it's working. Yeah.
Okay, so
Yeah.
it's working. Yeah.
Yeah.
So I
Please
repeat.
continue.
Okay, so in order to extract the equivalent circuit parameters from the magnetic energy of the machine, as I mentioned, so there is a sort of problem. It is a riddle which needs a careful attention. We have three unknowns. The inductance in the equivalent circuit, which has been indicated here, are the unknowns. And we need three arbitrary independent current excitation to create a set of three equations for the extracting those three unknowns. And therefore, the entire process shall be repeated 3 times for extracting the inductance values, which are indicated here. So this slide is summary of what we have discussed for the calculation of the motor equivalent circuit parameters. The formula for the rotor resistance calculation are illustrated. The formula for the stator resistance is not listed here, as it is a straightforward and it can be found in any textbook. So knowing the resistance of the equivalent circuit, the three inductances are the known values, basically. So I have calculated the magnetic energy equation for three independent excitation, as I mentioned in earlier slide, and the relevant equation for those three independent excitation are listed in the bottom of the slide. In this equation, I have defined three constants, Ks, Kr, and Km, which these defined constant represents the stator inductances, rotor inductance, and magnetization inductances. And once I have the equivalent circuit parameters, all the parameters are determined from the previous slide based on the discussion on the previous slide. We can then calculate the required performance parameters. So inputs to the circuit, the equivalent circuit, are going to be the applied voltage and mechanical power, which is considered as a load. As an example, looking at these two formulas, knowing the mechanical power and input voltages, the slip is going to be obtained from the first formula. Knowing the slip, power factor is then calculated from the second formula. Similarly, other performance parameters are calculated. So that was about how what is the analytical method. To investigate the accuracy of the analytical method, a set of sensitivity analysis is also I have performed on the design parameters of the studied machine. In each analysis, the performance parameters of the studied machine, including the slip, efficiency, power factor, and output power under nominal torque against simultaneous variation of two design parameters, are obtained using the analytical model and 2D FEA. The errors of the estimated performance parameters of the analytical model against the 2DA for such sensitivity analysis is calculated to make sure the accuracy of the proposed analytical method. These flowcharts basically illustrate such a process. As listed in this slide or this flowchart, the design parameters are considered the stator slot fraction in a slot pitch, rotor a slot fraction in a slot pitch, windings turns per slot, air gap lengths, and inner to outer diameter ratio, which I have indicated with lambda. The sensitivity analysis is implemented on this motor initially designed for the EV application purpose. It is basically the same 40 kilowatt 8-pole axial flux induction motor from the previous slide. The table lists other design parameters and a specification of the machine. So as I mentioned, is a duplicate of earlier presented table, but also I have included these design variables in the bottom of the table. This figure illustrates the output power, power factor, efficiency, and a slip of the studied machine obtained from the 2D FEA on the right side, as well as the errors in calculation of the performance parameters when computed using the analytical method on the left side. It was found that the main contributing factor in deteriorating the accuracy of the analytical method is high level of the saturation in the yokes. As shown in the figure on left side, this phenomena is most visible in the low number of turns and high number of lambda, high number of ratio of the inner diameter to the outer diameter. In order to address this problem, in this optimization process, I have put a constraint on the maximum magnetic flux density which is allowed to flow. And in the search space of the sensitivity analysis, such areas are presented by those black crosses, black cross marks, which I have indicated in this figure. Anyway, observing these simulation results confirm that the high accuracy of the proposed analytical method is visible, as well as reaching an error less than 5% against a 2D FEA in performance prediction of the studied axial flux induction method. So that confirms suitability of the proposed analytical method for the optimization purpose. So far, we have validated our analytical model. Therefore, it's time to implement the optimization using the presented model, the presented analytical model. We will consider different optimization scenarios. First, optimization of the motor for operation at a nominal point. Second, optimization of the motor for a specific for operation during a specific driving cycle. In this slide, I talk about the optimization of the studied axial flux motor for operation at a nominal point. This sort of flowchart shows that. GA is used as the optimization technique. Objective function is the maximum power density or minimum volume of the minimum volume for a nominal power. Maximum power density or a minimum volume for a nominal power. They are equivalent anyway. The implemented constraints are nominal power, maximum flux density in the teeth, maximum flux density in the yoke, minimum nominal efficiency, minimum nominal power factor. One more comment is that it is important to understand that in the design of an electric machine or electric motor basically here, the performance parameters are not only a function of the machine dimensions, but also are related to the control strategy. Consider the control strategy in optimization. The control strategy is applied as a constraint. In fact, the optimization is performed first with no constraint for operation at a nominal point. In the second optimization, which I'll introduce, everything is considered similar to the first case, except that the MTPA, maximum torque per ampere, operation at nominal operating point is forced as a constraint. Let's start with the optimization for the nominal point with no MTPA as a constraint. It is possible to simply leave the operation condition unconstrained in terms of control strategy, so that the optimization process chooses the level of the field beginning of the motor itself. The optimization variable to address these constraints are number of turns per slot, outer diameter, inner to outer diameter ratio, a slot width to the slot pitch ratio, a stator to yoke ratio, and height to width ratio of the stator slots. A stator slot fraction that I'm considering here. Alternatively, it is possible to optimize the motor in a way that the motor operates at the maximum torque per ampere at nominal point. In this case, the motor nominal power is obtained through a minimum amount of the current. That's the MTPA condition. So the optimization variables are similar to earlier case, but to satisfy the MTPA constraint, the number of turns per slot is no longer an optimization variable. It is therefore calculated to match the nominal power and MTPA. The associated formula for calculation of that one is listed on the bottom of this page. These optimizations that I discussed, based on what I've discussed, these two optimizations are run as per what we have discussed for operation at the nominal point with and without MTPA constraint for 3 different motor ratings, 3 kilowatt, 10 kilowatt, and 40 kilowatt. That leads to a total of 6 optimized design number from 1 to 6 in this slide. Also in this slide, I compared the performance parameter of these optimized motor. These design achieve the minimum volume as the objective function has forced that one, as well as the constraint of the predefined minimum efficiency of 80%, which I have defined. The performance of the optimized motor are also validated against the 2D FEA as shown in the Fig 15. Looking at this design, the maximum power density for all 6 optimized designs are also listed. In Fig 16, also in the bottom of the page, the feasible operating points in ID, IQ plane for all designs also listed. So this is a summary of the result that I have mentioned. Anyway, I don't want to dwell on the details of the result, but I would like to highlight some observations here. Looking at this design shows that a higher voltage limit is achieved in the expense of higher volume or mass. Higher voltage limit basically is achieved in the expense of the higher volume or mass. The MTPA design have a wider operating voltage range against those of the design with no MTPA constraint. That's what is observed on the Fig 16. It is seen that in MTPA motors, the voltage limit region, the nominal current, the voltage limit region, the nominal current, and the maximum torque per ampere curves are going to collide or reach at the same point, which confirms the validity of the designs that you can see in these points. The high maximum torque in MTPA design compared to the no MTPA constraint design also is as a result of, or as is an indication of the over design for our machines. That's what these results basically convey basically. So we have discussed the optimization of the optimal operation at nominal operating points. Now I would like to obtain the motor as a, I would like to optimize the motor as per a specific driving cycle. In fact, in this section, I would like to emphasize the motor design when I'm considering a specific load for the machine and see how that one is going to be different from what we have discussed. So the objective function of the optimization is the minimum volume of the motor as before, but the performance which should be met is the energy efficiency of the motor over its driving cycle operation. This efficiency, the energy efficiency, is the ratio of the motor output energy to the input energy over the entire driving cycle of the motor. The other thing that I need to mention is that all design variables are similar to before. Also, the design constraints are the same as before, but we have relaxed the restriction in the nominal power, because the nominal power doesn't mean anything at this is for that specific application. Again, we consider the optimization with and without MTPA operation at a nominal operating point. That's what we have designed, and this we have decided to do. And the optimization are performed for 3 common driving cycles as illustrated in this slide: highway fuel economy test, urban dynamometer driving schedule, and New York City cycle. To do so, I need to consider the vehicle dynamic model to extract the operating condition or torque speed points for each driving cycle. In fact, the operating points are extracted based on the motion equation and transmission coefficient of the vehicle. I have run the optimization as we discussed in the previous slide for 3 different driving cycles. Designs 7 to 9 are the 3 driving cycles with no MTPA constraint. In this slide, what is illustrated is the efficiency and the power maps of the driving cycle-based optimized motor without MTPA constraint consideration over wide range of the torque and speed range. Also, the capability curves and the operating points also illustrated in the first row. In this slide, the efficiency and the power maps of the driving cycle-based optimized motor, this time with MTPA consideration, are illustrated. The 3 different driving cycle-based optimized design also numbered as design 10 to 12. And the MTPA, one thing that I shall mention here, I have used the word with MTPA constraint. The MTPA operation is additionally applied for the operation specifically at nominal point as a constraint. That's a difference with the previous one. So it wasn't in the previous case. So it is seen that the driving cycle-based designs cover the entire, looking at these 2 slides, this one and previous one, basically Fig 19, it is seen that these driving cycle-based design cover the entire driving cycle operation points, and all design motors exhibit high efficiency, more than 90% for the majority of the efficiency map points. And the overload and capacity of the motor are modeled as the also modeled in the optimization to give us some flexibility in terms of the achieving higher power density or lower volume. So that's what we have done, and I have presented some results. Now I would like to have further discussion around the optimized motors and the observations to indicate the advantages of the proposed approach. This slide compares the design 3 40 kilowatt optimized motor for the operation at a nominal point against those driving cycle-based optimization designs. So by looking at Fig 20A, in the case of HFET and UDDC driving cycle, design 3 cannot operate at some of the desired points. The infeasible operating points of design 3 are illustrated with cross marks in figures 20 and 20B and 20C. Again, by looking at the figure 20A, in the case of NYCC driving cycle, the energy efficiency of the motor is about 89%, which is lower than the 90% limit. So that also has not been satisfied. Also, comparing the result for the design with and without MTPA considerations here, it is seen that MTPA designs offer a slightly better efficiency for the operation of in the driving cycle with higher number of operating points in lower speed, such as looking at NYCC driving cycle. And the other thing is that in general, both with and without MTPA design for the driving cycle-based case offer rather similar efficiency over a specific driving cycle. These are the observations based on the simulation result that I presented. Also, I would like to list some further observation as per the presented result. It was found that the driving cycle-based design is most appropriate for the EV application, and it is going to ensure the minimum design volume as well as the coverage of all torque speed operating points in a driving cycle of a choice. All driving cycle-based designs cover the entire driving cycle operation. As such, the over-design is also going to be avoided. That's one important aspect. Another one important aspect, basically. Also, it was found that an increase of the efficiency is achieved by performing an optimization over the driving cycle compared to a single point optimization. All design motors exhibit high energy efficiency of more than 90% for majority of their efficiency map points. It is seen that the overload capacity of the motor can be easily modeled in the driving cycle-based design. A non-optimized motor design may not also meet the requirements of the driving cycle. That was another important observation. It is seen that considering the MTPA constraint for the optimal operation of the motor at nominal point leads to a wider operating range and a wider control. In design with no MTPA as a constraint, maximum torque compared to the nominal torque is reduced due to the saturation in a speed lower than the nominal speed. Also, it was found that MTPA as a design constraint ensures a simpler control of the motor. Generally, it's because in MTPA design, the operating current in a speeds lower than the nominal speed is similar to the nominal point operating current. So the motor flux in those speeds is rather similar to the nominal flux, and hence saturation does not occur in those points. Not having a luxury of no saturation in speeds in lower than the nominal speed leads to a more complicated control strategy for designs with no MTPA. At the end, I would like to list some conclusions as per our discussion and the case study today. Most scenarios of we can conclude that most scenarios of the machine design optimization deal with multiple objectives and constraints beside the classical machine performance ratings like efficiency, torque ripple, power factor, power to torque density, cost, or other objective. Further objectives like control strategy and driving cycle of the machine could be considered in the optimization purpose. Other possible objectives also could be included, which we haven't discussed, such as radiated noise, robustness, etc. also could be investigated. That's another thing that should be considered in the future research. In the machine design optimization, both scenarios and respective solutions are going to be rich in variety, considering different aspects and scenarios. As a consequence, optimal design must be found case by case, and no universal machine design exists that can be considered for global optimization purpose. As the electric machine design, the other thing I can conclude that the electric machine design encompasses multiple topics of physics, mathematics, and computer science. It is expected that the innovations from various fields influence this field of research as well. So that's another thing should be considered. Although the other thing is, although significant advances in multiple fields has been allowed to do the optimization in a better way, but engineers should also be able to find a right balance regarding computational effort and the modeling accuracy. So in that case, I can say the expert input from an electrical engineering point of view is required to properly address the electric machine design optimization problems. Expert inputs is also necessary to develop and evaluate techniques for solving the scenarios and to check reasonableness, as well as the reasonableness of the obtained result, as well as the trade-offs. And finally, various heuristic optimization algorithms, such as a genetic algorithm and particle flow optimization or other methods, are the interest of the electric machine designs. A list of references used for this presentation is presented in this slide. I shall mention that I tailored the discussion around the case study within the available time of around 50 minutes. So I skipped some aspects like considering saturation and loss calculation for this case study. However, you shall be able to find more information about the case study in reference 5 listed here. And thank you for your attention. I would be happy to answer any question on my presentation.
Okay. And many thanks again for Dr. Amy's excellent talk and during the past 1 hour. And we all enjoy a lot during this in his talk. And from the perspective of the modeling of the axial-flux induction motor to the optimization techniques for the inductor motor, particularly for the electric vehicles. And as also we have seen many simulation effective simulation results to show the proposed methods is very effective, and many advantages existing in the system. And thanks again for Dr. Amy's talk. And if anyone has questions, we can have fair, free discussion with Amy. Okay, so now, first of all, I have 2 questions. Okay, Amy. First of all, because your topic is focusing on the optimization of electric machines for induction motor. So my question is, can your proposed optimization techniques in this in your work be applied to any other electric motors or not? Sorry, Amy.
He's muted.
Yes,
Hi, please unmute it.
Yeah, can you hear me?
Yeah, we can. Yeah.
Okay, so it is, yes, applicable to any optimization of any type of machine, considering the methodology of the optimization methodology is general, could be optimized based on a specific driving cycle and a specific control strategy. From that aspect, yes. However, the analytical method for that purpose should be adjusted to the new machine, because the analytical method was developed specifically for the axial-flux induction machine. Even for the radial flux modeling, there are some adjustments that should be also considered. But it is general. The optimization methodology, overall, yes, general.
Okay, all right. Thank you. And my second question is, because in your work you have provided sufficient simulation results, and my concern is if you want to implement your proposed method in the real electric vehicles, So can you please, predict or give some, ideas to show some, technical difficulties if we may meet when we implement your proposed methods to the practical electrical vehicles?
Yeah. As you mentioned, in practical, the whole scenario could be a little bit different. So what I can tell, this axial-flux induction machine has not been really popular, and you don't find much application in real work. However, there has been a company in Sydney who has been developing this type of motors, and I am collaborating with them on this sort of motor, and we are looking for some fabrication of some type of these machines. They have built this type of machine, and they have had some issues with the simulation validation of the efficiency map they have extracted experimentally, which is different from what we get in the simulation, basically because of different sort of point of views. First thing is that you really can't apply the same sort of control strategy when you are trying to generate the efficiency map as you do in the simulation. There are some simplification that you need to consider, and that cause some sort of errors. As well as, again, end binding effects. And then, for example, one of the problems with this sort of motor we have to make sure, for example, if we are designing the motor for 0.5 millimeter of the air gap, to make sure always it is going to be 0.5 millimeter air gap. There are some technical issues when fabricating, but that one also could be considered and studied case by case. And then once you do the fabrication, you can adjust your result to make sure you are doing the right thing. But overall, this method, the presented method, analytical model, is reliable to some extent if it's not going to give you a really highly saturated machine.
All right. Yep. Thank you. Thanks very much.
No
Amy.
worries.
So I learned a lot from your, talk. Thank you very much. So,
thank you. Thanks for the opportunity. Yeah.
So if anyone has questions, please feel free to ask, so we can have some, free discussions here. Yeah.
Okay, I have a question. First of all,
Yes,
thank you very much for your presentation. That was really interesting. Regarding the optimization, especially the GA you have used in this research, I would like to know that how sensitive your system or the optimization routine is with respect to the initial guess of the parameters.
Okay, so the initial design, as I mentioned, okay, something regarding the optimization of the machine, you need to be very careful. You need to have a good initial guess of the motor. So basically, there are sizing equations, as I mentioned, which give us the rough estimation about the design for a specific application. We have used those sizing equations to come with a good sort of initial design, and from there we have done the optimization. Honestly, we haven't really checked how sensitive this optimization process has been against GA, but we haven't really, based on what initial design, we haven't seen much issues in terms of optimization, because once the design has been optimized, we have tested against the finite element, 2D and 3D finite element, mainly 2D, and the result has been satisfactory. And of course, each time it gives, rather different sort of optimization, but the motor has been more or less similar, considering a huge number of points to be tested for the performance parameters. I'm not sure if I have answered your question or not.
Yeah, thank you very much. I got the point.
Okay.
So do we have anyone having questions? So please feel free to ask. I can see now, except me and Amy, there are 9 members, 9 attendees in our seminar. So please feel free to ask questions. Paresh, Ahmed, Feathers, Shoaib, and Moed.
I can see some familiar. Yeah, yes, please.
I was wondering, maybe, first of all, thank you for your great presentation, Amin, and I was wondering, maybe, have you checked other optimization algorithms other than genetics, maybe for the purpose of, the speed of the results or the accuracy?
Yeah, thanks for the question. I guess your question is again aligned with what Amir mentioned. No, we haven't tested. Okay, let me put it this way, which I mentioned in my conclusion also. In optimization of the machine, although you use these tools, GA or PS or other tools, it is very important to have the designer inside, and you need to validate those designs. For our case study, we were relying on our understanding on the design itself rather than what GA particularly gives us as a sort of black box. We were not looking at that one. It doesn't really, you most probably won't be satisfied with some such sort of optimization. It is expected you to have an initial design, and also once the optimization algorithm gives you the design to be sort of to be evaluated by the designer. No, we didn't test any other sort of optimization techniques because we were relying on what we were not really much relying what GA was giving us. We were testing in from different aspects to make sure we have right optimized design. But it would be good to, yes, further investigate other sort of optimization tools, as well as looking at the robustness of the optimization, which Amir mentioned earlier, but we didn't really consider that one, which could be a further investigation.
Yeah, okay, thank you. The reason I ask this is that genetic algorithms has some kind of problems, especially over globalization variables. I believe you have solved it by, as you mentioned, a good guess regarding the initial design.
Yeah, that's what I mentioned. You can't look at these optimization tools as a black box, especially for design of the machines. It needs an insight of the designer to make sure you are doing the right things. Looking at the tools we have used, we were using the finite element tools. We were using the optimization tools. Both of them are really tricky in terms of giving you the result. You need to have a good understanding of the results that you get. Even in the finite element, you put some sort of inputs to the software, and then it gives you some results. But whether those results are reliable, understandable or not, that needs a designer input to make sure you are doing the right things. Yes, we did it with a good initial guess to make sure we are achieving a global optimized design, basically.
Yeah, thank you for your explanation.
No worries.
All right, thank you, Amy, for your good, response to our questions. And now let's limit our question to the final one, because the time limit. Now we have Dr. Zhi from Finland. So, Zhi, do you have any question, regarding our talk? Because I know you are doing research on the electric machines.
Oh, hi. Thanks
Hello.
for your presentation. I'm a new student here, so I'm pretty clear about your topic. And yeah, that's just good for me to study that. And I'm keep learning that. Thank you. I have no question about that.
All right, no problem. Thank you. So, is anyone have a question? So possibly we can, have free discussion after this talk. So because of the time limit, so I would like to end, our talk today. And finally, thanks very much again for Dr. Amy's, presentation this afternoon. We all enjoyed, a lot during the past 1 hour and a half. So, and we look forward to, future, online seminar in the next few months. So thanks very much for your attending, seminar this afternoon. See you next month.
Thank you. Thanks for the opportunity and see you.
Thank you, Amy. Thanks very much.
Bye.
Bye-bye.
Bye.